All right, today we're tackling a massive question. It sits right at the intersection of geology, engineering, and, well, economics. How do we actually prepare for a disaster? We're going to do that by looking at the science of seismic hazard analysis.
So let's just jump right in with the big one. Imagine you're an engineer. You're designing a critical piece of infrastructure, like a bridge or a power plant. How in the world do you build it to survive an earthquake that might not even happen for another 500 years? And this isn't some abstract thought experiment. It's a very real, very high-stakes problem that scientists and engineers have to solve every single day.
You know, on the surface, the goal seems pretty straightforward, right? Build things so they don't fall down in an earthquake. But the reality is this constant, tricky balancing act. If you design for the absolute worst case, most powerful shaking imaginable, your costs are going to be insane, maybe even impossible. But if you design for something less severe, you save a ton of money, but you're also accepting more risk. So figuring out exactly how much shaking a building needs to handle, that is one of the toughest and most important jobs in all of earthquake engineering.
So, if you want to get a handle on what the future might hold, you've got to look to the past. And that means we have to become geological detectives, piecing together clues that ancient earthquakes left behind. A lot of this detective work actually starts way up high, from the air. Geologists use aerial photos and some really advanced remote sensing tech to spot the scars that past earthquakes have literally carved into the Earth's surface. This gives them that crucial big-picture view of where the major faults are hiding. Then, it's boots on the ground looking for direct evidence. And you can find some incredible things. This cliff of ice, for example, is what's called a false scarp. It's a feature that gets created when one side of the ground lurches up or down during a quake. And by measuring how high these scarps are, scientists can get a really good estimate of just how big that past earthquake was.
But to get a really detailed history, geologists do something pretty amazing. They will literally dig a trench, just like this one, right across a known fault line. Then they get in there and meticulously map out all the layers of soil, looking for places where they've been broken and shifted by past earthquakes. And get this, by carbon dating bits of organic material they find in those layers, they can build a timeline of quakes going back thousands of years. It's incredible.
So you take all these different clues and you start to piece them together. Each one gives you a different piece of the puzzle on a different timescale. Modern GPS can measure ground movement down to the millimeter, right now. Instrumental records go back about a century. Written historical records can take us back a few thousand years. And the geology? Well, that can tell a story that's millions of years old. It all combines to create one cohesive history. Okay, so you've done all this detective work and gathered a mountain of historical data. Now what do you do with it? Well, the first method for turning this data into a real-world design is what we call the deterministic approach. I prefer to call it the what-if approach. This method, sometimes called DSHA, is very logical and straightforward. Step 1, you identify all the nearby faults that could cause a problem. Step 2, for every one of those faults, you figure out the closest it gets to your construction site. Step 3, you do the math to see which one of those faults would create the most intense shaking right where you're building. We call that the controlling earthquake. And finally, step 4, you design your structure to withstand that one single worst-case event. Simple as that.
But what if just planning for one single worst-case scenario isn't telling you the whole story? That brings us to our second method, the probabilistic approach. This one is all about playing the odds.
At the heart of this whole approach is a principle called the Gutenberg-Richter recurrence law. Now, it sounds really complicated, I know, but the idea itself is actually super simple, and it's something you probably already feel is true. Small earthquakes happen all the time, but the really, really big ones, they're incredibly rare. And this relationship holds true pretty much everywhere on the planet.
So, you see the difference here? Instead of focusing on just one controlling earthquake, this probabilistic method, or PSSA, it takes everything into account. It considers all the possible earthquakes, the big ones that are far away, the small ones that could happen right underneath you, and everything in between. And it combines all of that with the actual probability of each one ever happening.
All of that complex calculation boils down to this one incredibly powerful graph called a seismic hazard curve. It's maybe the best tool we have for summarizing risk. Here's how it works. The bottom axis shows the intensity of ground shaking, from pretty mild all the way to severe. And the side axis shows the annual probability. So you can pick any level of shaking, go to the curve, and it'll tell you the odds of experiencing at least that much shaking in any given year. It just gives you a much more complete picture of the danger.
So we have these two really powerful scientific tools, but they both lead us to a final question that, frankly, science can't answer on its own. This is where the decision-making process moves out of the lab and into society.
So let's put these two philosophies side by side. The deterministic approach, its biggest strength is that it's simple. The rules are clear. Its weakness, though, is that it never tells you how likely that worst-case scenario actually is. Now, the probabilistic approach is much more thorough. It factors in how active different faults are and gives you a really consistent measure of the hazard. But, and this is a big but, it forces you, the user, to explicitly choose what level of risk you are willing to live with.
And that, right there, that is the million-dollar question, isn't it? The science can give you the odds, but it can't tell you which bet to take. What level of risk is acceptable for a single-family home? What about a hospital or a nuclear power plant? The answer is probably different for all three.
This quote just absolutely nails it. A seismologist can create that hazard curve and hand it to you, but they can't point to a spot on the curve and say, there, build for that. Deciding whether to spend the money to protect against an event that might happen once every 500 years or one that might happen every 2,500 years, that's not really a science decision. It's an economic decision, and it's a political one.
And I want to leave you with one final sobering thought. Consider this real-world example. Back in 1992, any probabilistic analysis of the Maharashtra region in India would have told you the chance of a big, damaging earthquake was extremely low. But low probability doesn't mean zero probability. The very next year, that tiny, unlikely possibility became a reality, and it caused widespread destruction. It's a powerful reminder that when we're dealing with the forces of the Earth, we are always ultimately just playing the odds.